So back to the main topics. So I'm going to wrap up generation. We're talking about generative adversarial networks last 2 weeks ago, and I think I sped through the end because we're running out of time. But let me just recap GANs, and I'm going to talk about diffusion models. I'm going to wrap up generation, and then we'll go into the next topic on transfer or transference. So recall the key idea of GANs is that you want to do likelihood-free learning or likelihood-based learning, which is that you estimate P of X, either through autoregressive model, variational autoencoder, and so on. But typically, just doing likelihood-based learning is going to be very difficult. It's difficult to capture P of X. And if you estimate P of X really well, and your space is super high dimensional, high P of X might not actually correspond to realistic samples. And the whole idea of GANs is to, instead of doing likelihood-based learning, go into likelihood-free learning. And we actually generate samples without having to estimate P of X. And a key idea in GANs is that instead of estimating a data distribution, I'm just going to estimate a classifier that can distinguish real data from the world and fake samples that you generated through your model. Essentially learning this two-sample test to distinguish whether these two are from the same distribution. And therefore, we saw that GANs involve two parts, a generator and a discriminator. The generator takes in some noise variable Z or some latent variable Z, goes through some neural network parameters, and generates your data X. And that tries to generate images or text and so on. The discriminator tries to distinguish between real samples in the world and those sampled by your model, right? Distinguish real samples from the fake ones that you generate by your model. And the objective function is actually very simple. So we start with the discriminator. You're going to try to maximize this cross entropy. So assign high likelihood of the probabilities of those data points actually from the data, and assign low probabilities to the points that were actually generated by your model. Essentially, this binary cross entropy classification. And the generator would just do the reverse, right? It tries to fool the discriminator. It should basically just do the reverse. And if you actually look at this objective function, the first term, which is just the likelihood that a discriminator assigns to real samples, that's independent of the generator parameters. So that goes away. So essentially, the only objective for the generator is to make the discriminator assign high likelihood to generator samples, like fool the discriminator. And you can actually train this very easily, right? You can train it by taking a bunch of real data points X from your data set. You can take a bunch of noise vectors Z or latent variables that's probably sampled from some Gaussian. You basically train ultimately both the generator and the discriminator. Right, the generator parameters, you're going to update using stochastic gradient descent to fool the discriminator, make the discriminator assign high likelihood to generator samples. And for the discriminator, you're just basically doing binary cross entropy classification between real samples from the data set and those generated by the generator. And these things are typically harder to train. You've got to fix one side, train the other, you've got to fix the other side, train the other, and alternate. And although they can create very high quality samples, it might not be worth it to train these from scratch. It's typically quite hard to train. This is not working. Yep. So anyways, we've talked about generative models so far. We saw likelihood-based approaches. That all involves estimating P of X. P of X is typically very hard to estimate in high dimensions. So we saw VAEs, which approximately estimate a P of X using this variational lower bound. We saw autoregressive models that exactly estimate a P of X using a chain rule by decomposing P of X into P of X at every time step. We saw normalizing flows, which also allowed us to exactly estimate P of X through invertible transformations. And finally, for GANs, they don't actually estimate P of X, but they just distinguish real or fake samples. So that's called likelihood-free. And each of these, as we recapped, have pros and cons. VAEs are typically fast and easy to train, but because of the reconstruction objective at the image side, they typically generate images or text of lower quality. Autoregressive models are easy to train and give exact likelihood, but it's actually slow to sample from because you got to autoregressively capture P of XT given XT minus 1. Normalizing flows are also easy to train and they give you exact likelihood, but your architecture is very constrained, right? You need the generator and the encoder to be invertible maps of each other. And that doesn't give you a lot of flexibility in designing your architectures. And for GANs, you have high generation quality because you're not actually doing any reconstruction, but it's very hard to train. And you also can't get features. There's just a latent variable Z to data X, but there's no way to take X and encode it back to Z unless you do something special. So we look at GANs. Again, we have this generator and a discriminator, right? The generator has to generate from a noise vector or a latent variable high dimensional images. And all the discriminator has to do is to distinguish a real and a fake image. So you expect that a discriminator has a much easier job than a generator, right? And in fact, in the beginning, when a generator is rubbish, random parameters, Z is noise, it goes to initialize random parameters. X is going to be basically noise. So the discriminator trains very quickly. You're just going to have a very easy time distinguishing real images from fake images. And the generator is basically not going to train at all. So typically, there's a bunch of ways that you have to, a bunch of optimization hacks and heuristics that you have to apply to get both of them actually training. Yeah. But I'm going to point out some literature towards the end of generation so that you can look at some tricks on training GANs. Okay. And as I promised, I'm going to get into one last generative model, and that's called diffusion models. And diffusion models have really been on the range recently, right? They've been able to generate really high quality images, sometimes condition on text. So the whole idea of diffusion models is that I'm going to, again, like normalizing flows, do a couple of steps sequentially. I'm going to start with the image. I'm going to slowly add noise to the image. Right? So x0 is my original image. At every time step, I'm going to slowly add noise to my image. That gives me x1, x2, x3, all the way to xt. If I go through enough steps of adding noise, it's going to become more and more blurry, and eventually it just becomes full Gaussian noise. Right? You can't distinguish the original image at all. So that's the easy process. That's called the diffusion process, slowly adding noise to your model. What's interesting then is that if you slowly add noise to your model, you should also be able to slowly remove noise from your model. Right? It might be hard to add noise once and corrupt your image and have it invert, but if you add noise slowly and remember each checkpoint, you should be able to reverse the noise slowly as well. And that's the key idea of diffusion models. You add noise slowly in the diffusion process from x0 through xt. With t being large enough, you get random noise vector. And the reverse diffusion process basically tries to learn parameters that reverse the complete noise back to these intermediate steps and back to the original image. So we're going to use two terms, right? The first term is called encoding or diffusion process. That takes in my image and slowly adds noise to it. And we're going to denote this diffusion process or adding noise as Q. All right. So my Q for a next time step xt, given my previous time step xt minus 1, is going to be some Gaussian centered as some scale version of xt minus 1 with some variance. And it's going to be some hyperparameters alpha t that basically tells you how much noise I add at each particular time step. Right. So centered at the previous time step, that's your mean. You're shifting around, you're scaling it, and you're adding some noise within that region. That's the encoding via noise, adding noise. And this alpha t is known as noise parameters. And we're going to get into a discussion on alpha t later, but it should not be surprising to you that there should be a sequence to designing how much noise to add towards the beginning and then towards the end. But we're going to talk about these noise parameters a little bit later, how to choose them. So that's encoding. For the decoding process, so in the encoding process, there's no parameters. It's fully deterministic. Well, not deterministic, it's random, but there's no learning involved, right? It's predefined and you can start adding noise to it. It's the reverse process, actually decoding from noise to data, where you actually have to train parameters, right? So we're going to denote this as P sub theta, where theta are some parameters of perhaps a neural network that you want to train. So in each of this, I'm going to learn the joint distribution. That's P of x0. That's my original image through xt, which is the final super noisy image. And I can basically use an autoregressive assumption and factorize it into P of xt. That's the final noise vector. That should be just isotropic Gaussian, centered at 0 with unit variance. And all the subsequent translation stages from xt minus 1 to xt. So each of these steps slowly reverses one step of noise. You're going from xt, which is more noisy, to xt minus 1, which is less noisy. Right? So essentially, you're trying to decode from noise back to images by denoising. Okay, any questions about the setup so far? Okay, just a recap. Diffusion, adding noise, fully predefined. And to actually generate data, you go from noise sequentially back to a real image. And P theta of xt minus 1 given xt for all t are the parameters that you want to learn. So if you stop and look at this, this actually seems quite similar to variational autoencoders, or more precisely, a hierarchical version of variational autoencoders. Because at each step, given, for example, xt minus 1 xt, you have something closer to the real data and something closer to latent variables. You have an encoding process that encodes data to something closer to latent variables. And you also have this generative process from latent variables back to the real data. So it's going to be actually very similar to variational autoencoders. And the first method of deriving how to solve this is actually going to be also, again, variational inference. But there's some key differences. At least in the first version of diffusion models, the latent dimension, which is each of the intermediate steps, x0, x1, all the way through xt, they're all in data dimension, so pixel dimension. And that's one constraint. And if you recall, this is basically the similar constraint we have to normalizing flows, right? Because you started with an image, you have these invertible maps. For it to be invertible, the dimension had to stay the same. So again, a similar assumption. The latent dimension, each of these xt's are going to be equal to the data dimension, which is your actual pixels. The second assumption is that in autoencoders, we saw the encoder from something closer to the image latent variables Q was a variational distribution. It was what we learned using neural networks to approximate the actual distribution P, which is hard to compute. So the Q actually has some parameters, 5 or something. And we learned the encoder and decoder jointly. So in diffusion models, as I emphasized, the Q doesn't have any parameters. You don't actually have to learn the encoder. The encoding process is simply adding noise through some predefined process. So to be precise, the predefined is a Gaussian distribution centered around the output of the previous time step. And the third big difference is that we're also going to, well, this is kind of like a similarity, but essentially we're also going to start with something that resembles data and slowly make it closer to latent variables that resemble noise. And variational autoencoders also kind of do that, although in one step. So this is kind of a hierarchical version of autoencoders where you slowly add noise to make sure it resembles isotropic Gaussian in the final latent variable. So given these similarities to variational autoencoders, the way of actually solving these diffusion models, at least the first way, is to use variational inference. So again, I'm going to try to maximize the log likelihood of my data. That's P of X. That's, again, all I care about. And because we maximize P of X or model P of X, diffusion models are also a likelihood-based approach. So you know that P of X is very difficult to compute. You can't compute that exactly over all X. The integral over all X is difficult. We're gonna define the variational lower bound. And this is exactly the same derivation we had in variational autoencoders. Essentially, you're gonna take some simpler distribution Q, and it's a lower bound based on log P over Q, right? So the expectation of Q, log P, that tells me how well I can explain my data, P of X, under this simpler distribution Q, because my expectation is under Q. And this term in the denominator is going to turn out to be expectation of Q log Q. That's the entropy of Q, right? In variational autoencoders, we discussed that that's entropy of Q. It basically measures how simple Q is. So it's going to have a trade-off, right? You want to be best explain your data, log P, under the simpler distribution Q, the expectation over Q. At the same time, you want the entropy of Q to be small. You want Q to be simple. And again, we saw that we could derive this either through Jensen's inequality or through a definition of KL between Q and P. But again, for the full derivation, look at these two tutorials, which I'm also basing most of these slides on. So the big difference between variational autoencoders, as I mentioned, is that this Q in variational autoencoders, we started parameterizing with some parameters 5. So this Q is learnable. We want to learn the best Q that maximizes the variational lower bound. In this case, the Q that we're just going to choose is this actual encoding process Q, which is predefined by adding noise. Right? So you don't actually have to learn Q. All you have to learn is this P. So through some derivations, which I'm not going to get into, but again, the derivations are similar to variational autoencoders, and check out the tutorial. Optimizing this objective leads to 3 terms. The first term is this reconstruction term, right? And an expectation under Q of X1, so that's the very, very, very first step, the log likelihood of reconstructing my data, my perfect data X0, given my first step noisy data. Right? I want to be able to maximize the log likelihood of reconstructing my data X0, given the first noisy step, under the simpler distribution that adds noise to my data, Q of X1 given X0. And perhaps it should be clear that I quote out the first term because subsequently there's going to be a telescoping term from time step 2 all the way to the final time step. So again, in this reconstruction term, this is easy to optimize, right? Your parameters are P of theta. Again, Q is all fixed. All I'm learning is the denoising process, P of theta. I want to be able to maximize the likelihood of reconstructing my original image x0, just given the first image that I've added noise to as given by my noising process, the noising process Q. That's a reconstruction term. The second term, also similar to variational autoencoders, that's going to be a prior matching term. I want to make sure that the final time step, my distribution of P of xt, large T at the last time step, follows some prior that I defined. And again, the interesting here is that we know that P of xt with sufficiently long T of adding noise, P of xt is just going to be isotropic Gaussian. My Q of xt, which is the final step of adding noise, should also be isotropic Gaussian. And they actually found through experiments that this term just goes to 0. There's no learning involved in this term. As long as with sufficient number of time steps, you actually get a latent variable that is isotropic Gaussian. And this third step, this is the telescoping sum that I promised, summing from t equals 2 to the final time step. And this is what I'm going to call the denoising matching term. And this term seems a bit complicated, so I'm going to expand on it a little bit. Essentially, we've dealt with the very, very, very first time step, right? We know that the very first time step, P of theta x0 given x1, that's going to be just a reconstruction like variational autoencoder from qx1 given x0 back to P theta x0 given x1. That's the very, very first term. And now we've got to learn all these subsequent terms from the second time step to the very last time step. And essentially what the derivation tells us is that you want to learn a matching term between each of these P thetas. So each of the denoising steps from xt minus 1, from xt to xt minus 1. And I'm going to try to match it with something called qxt minus 1 given xt. We saw that qxt given xt minus 1, that's adding noise to it, was deterministic. The derivation tells us we should try to match it with this reverse diffusion process. The ground truth of what removing noise looks like. You want to make sure that each of these terms in pink are close to each of these terms in green, where the learnable parameters are each of these terms in green. Right. And I'm going to minimize a KL, sum over time step from 2 to t, expectation of under Q. So that's basically sampling the data points they've added noise to at each time step, right? Where t goes from 2 to capital T. So any questions about this so far? At least the intuition. This actually almost extends from hierarchical variational autoencoders. So VAEs we saw is we just x1 and x0 and x1. Right? So you look at all this and just assume that there's 2 time steps, x0 and x1. If you derive a variational autoencoder, you're also going to have a reconstruction and also a KO between x1 and P of x1. Right? That's basically variational autoencoder from x0 to x1, and we started diffusion models with just x0 and x1 also gives you the same two objectives. All I'm saying is that if you have multiple time steps in your diffusion process, x1 through xt, you also have a prime matching term for the very last time step. You have the reconstruction term for the first time step, and you also have these reconstruction terms for all intermediate time steps. You have prior for the last time step, and you have reconstruction in each of the intermediate time steps. Be sure that code out the x1, or at least the people who derive that code out the x1 for clarity, and they separate it out to the ones from time to the time. So both of these can be seen as reconstruction objectives, and this can be seen as the prior matching objective. So it's actually quite similar to a hierarchical version of variational autoencoders. Right, this part is a bit different because you've got to go backwards. And so this part actually gave 2 derivations. The first derivation, we don't have to go backwards, but that one in practice leads to a bit of a higher variance. But I'm going to post a tutorial and you can look through the details. The good thing about here is that, and we're going to derive this very soon, you can actually go backwards. So this Q over here. You have a Q, that's the encoding process. In VAEs, this is learned. So there's no way of kind of learning that backwards. Right? But over here, my Q is pretty fun, using adding Gaussian noise. So you can actually derive a closed form for the backwards. So this pink thing over here that you're trying to match with what you learn, this can actually be captured in closed form. So that's a cool benefit. Normally, if I did variational autoencoders, my Q would be learnable as well. I learn my Q and P at the same time. There's some parameters here. So it's not no way of defining the Q backwards. Cool. Any other questions about this? Okay, let me get a bit more detail on this denoising matching term. As we saw, you want to learn this P of theta backwards, so removing noise. And essentially, I'm going to try to minimize the KL between so-called the ground truth Q of removing noise. So this term, I'm just copying this over. The biggest thing that I got to define is this Q term, right? P of theta is my neural network. I can do using gradient descent. I'm going to try to derive what this Q term backwards will look like. So using Bayes' rule, I can express Q of t minus 1 given xt as the opposite, Q of xt given xt minus 1. And I'm going to have some constants, Q of xt minus 1 on the numerator and Q of xt on the denominator. So that's Bayes' rule. And then I basically got to just define what each of these terms mean. So Q of t given xt minus 1, that's just the process of adding noise. Right? That's the forward process, diffusion process. So that's fixed. That is basically a Gaussian with my previous xt minus 1 scaling and shifting by some noise with some standard deviation. So that's fixed. For this Q of xt minus 1 and Q of xt, a familiar trick pops up. That's a reparameterization trick. We saw that Q of xt can be defined either directly drawing from this Gaussian, right? But what you can also do, you can also just sample random noise epsilon, scale it by the variance or the standard deviation, and add the noise. So instead of sampling xt from this Gaussian distribution with that mean and variance, I can also just sample epsilon noise vector, shift it by the standard deviation, and add the mean to it. Right? Reparameterization. I can do the similar thing with xt minus 1, reparameterization. And subsequently, and I know that xt is just this Gaussian distribution. So essentially, you can show that the ratio of these three Gaussians, which are all normal distribution Gaussians, is going to be proportional to some other Gaussian, right? You can actually write this Q of xt minus 1 given xt, the reverse process in closed form. The mean and variance are going to be nasty symbols, but essentially the key idea is that it can be proportional to a Gaussian, where this mean and variance depend on your alphas at every time step. So that was the Q, the reverse process that you want to match. And we said that you want to learn the P. And the P is the reverse denoising process with the actual parameters data that you want to learn. So we know that my Q is a Gaussian and I want to minimize the KL between Q and P. I can also just simply define my P as a Gaussian. Again, similar to variational autoencoders. We defined our the KL that you want to match. We learned the mean and the variance of that encoder. So I'm also going to parameterize this as some Gaussian model. Usually in these cases, we don't care about the variance that much. We don't care about matching the variance that much. People typically care about matching the mean. So over here, you have mu q and sigma q that's fixed through a derivation. I'm just going to define my P of theta through some mean theta. So my mean is going to be learned and my Q is just going to be the same. And then you can derive that minimizing the KL between Q and P with the same variance essentially amounts to minimizing the KL between these two Gaussians. With the same variance. And that amounts to just minimizing the mean squared error between the two means. Right? The actual mean that we derived, that's mu q, and the mean that I define my model to be, that's mu theta. Okay? So key takeaway, this backward translation process, q xt given xt plus 1, that can be derived in closed form. That's going to be some Gaussian with some mean and variance parameters. That's fixed in closed form, approximately. And you want to learn this backwards model that actually removes noise. I'm going to also define that to be a Gaussian. I don't care about the variance that much. I'm just going to match the mean. All right, so you have, you end up with this objective. This objective that basically matches the mean data that you're learning at every step of removing noise with the actual mean. So what's the intuition for this? And what do these means actually look like? So we saw that Q can be derived in closed form with some mean parameter Q and variance. We saw that we're also going to parameterize our P of theta with some mean theta. So essentially what this mean of Q looks like is that it's going to scale all my XTs and with some with our alpha parameters, but essentially it's a function of both XT, which is the T that I currently get, and my X0, which is the perfect version of the image, X0. So what I actually want to define my mean to be is, again, just follow this as close as possible because we're going to minimize the mean square error between these. It's basically going to be xt and some function x hat theta. Essentially, given xt, which is a noisy version of my image, at time step t, how well can I reconstruct the original image x0? Right? You're basically just training a neural network to predict the perfect image x0 from a noisy version of that image xt at time step t. Right? That's basically what matching these means actually. And you want to do this over all t, right? Small t with less noise and larger t with more noise. So again, using this formula for the mu q, which is derived and predefined, and mu theta, which is what we chose the neural network to be, minimizing the KL divergence between these two distributions basically just amounts to minimizing the mean square error between the original image and your predicted version of the original image given some noisy version of it at all time steps t, summed up from at all time steps t summed up from 2 to the final time step. Yeah, so that's exactly what you get. That's how you kind of solve these diffusion models. Just to recap your reconstruction term, how you can reconstruct the very, very, very first image from the first time step. From the first time step which you added noise to, you have the prior matching term, making sure that the final latent variable is fully isotropic Gaussian. And you have all of these intermediate time steps that basically say that at any particular version of xt, which I've added noise to, given by the distribution of adding noise q, at any of those xt's, I should be able to train a model that recovers the original image, right? So that's this last denoising matching term. It becomes an optimization problem over all time steps from 2 to t without the first one, because the first one was captured in the reconstruction term. And for all the subsequent time steps, under my distribution of xt of q, so under my added noise version of the image, how well can I reconstruct the original image as measured by mean squared error? Okay, any questions about this so far? About each of these 3 terms or about the denoising matching term that we just went into detail? Okay, one quick note, because I've talked about this alpha t quite a bit, and it's actually something that goes into what these how to choose these alpha t's. Essentially, you want to choose these alpha t's. You want to add smaller noise at the beginning of the diffusion process. And you want to gradually increase noise when the samples get noisier. So if you just start with the image, it's actually a perfect image. Just add a little bit of noise to it slowly at the beginning. And once you're already in like latent variable space where the image looks like some Gaussian, you can freely add more and more noise to it. And there's 3 interpretations. That's actually the first one they talked about. Essentially, you're based on derivation, you're actually learning a model to predict the original image x0 given some noisy image xt at time step t. That was the first derivation, right? There's actually a second related derivation, which is also pretty cool. You're basically learning a model to predict the noise epsilon t added at every time step t, right? And you can kind of see these 2 are equivalent. If you have the noisy version of the image and you reconstruct the original image, it's going to be equivalent to just predicting how much noise was added, epsilon t, and then removing this noise, right? Because removing the noise can be fully predefined. I'm not going into more detail, but it's also a cool derivation here that you can express. Again, in the reverse diffusion process, we saw that you're matching the means of my mu q and mu theta, right? You can also express mu q as a function of xt, the noisy version of the image, plus the noise that you added, epsilon 0. So you can actually match your means with a model that you learned to remove the noise as something that just predicts the noise instead of predicting the full version of the noisy original image. So 2 related definitions. You either reconstruct the original image that's perfectly clean from subsequent noisy versions from it, or you predict the noise added at every time step. And both of these can be used to solve diffusion models. And actually, very quickly, one last interpretation, which is if you look at some related work, some of them motivate diffusion models from this perspective, is call them score-based models. And this is a third definition that also allows you to rederive diffusion models. So the third interpretation is that you want to learn a model to create the score function. So what's the score function? The score function is that we talked about these likelihood-based models. They basically want to model P of X. The score function is a unique property, is unique quantity, log P of X. So first taking a log of it, and then taking a gradient with respect to X. And you can actually derive diffusion models based on just this equation. And basically learning a model that if you know what my score function is, my gradient with respect to X log P of X, just learning a model that given X recreates a score function using mean squared error. So this is actually not a very easy problem. There's a long history of doing it. It's basically called score matching. But basically, you can actually do this, right? And just give some intuitions on score functions. This could be my P of X, some weird multi-normal distribution. The score function doesn't have to be normalized, and it actually looks a lot simpler. Right? Just give some intuition on what these score functions are. And visually, what these score functions basically look like, if this is your distribution that you want to capture, that's P of X, it can be, again, very complicated. My score function is basically this kind of vector field that basically tells you at every point what direction I should move towards to maximize my log P of X. What direction I should move towards is essentially the gradient, right? So if I have some points over here, I'm going to try to move towards here. That corresponds to this peak. If I have some functions, if I have some points here, I want to move towards this part, that's this peak. And likewise, if I have some points here, I want to move towards this part, that models this peak. Now the score function can be seen as this map across all X directions in which I should move towards to get to high regions of log P of X. So that's the score function looks like. So essentially, people found that you can actually, again, a really good derivation tutorial by these folks. Yes, there are some relationships. Specifically, instead of MC sampling, you do some other form of sampling, which I'll get into. But it's actually very similar, yes. So again, these folks gave you a very nice tutorial. So you can actually train a model that takes in X with some parameters data to try to recreate your score function, right? And if you can do that, then you basically have a good estimate of my score function. And you can actually sample more data based on some sampling approach. I'm not getting into the details of this, but essentially looks like this, right? You can start with any point, and by basically following the direction of the gradient log P of X, you can actually go to higher regions of P of X. Right? And if you get to high regions of P of X, if your estimates of P of X are good, you're also going to be able to go to regions of high density images and realistic images. And the main part that links score function estimation to diffusion models is actually this issue they found in these score-based models, right? You can first take some data samples, some of high region, some of low region. That's just X within your P of X. Do score matching by basically estimating a function that takes in X with some parameters data, estimates the score function. That should be as close as possible to the ground truth score function, and sample according to these sequences to get new samples. And the main issue is that if your data density is very sparse, right? If you're actually working in the space of natural images, you have very, very high dimensional data that lies on some low dimensional manifolds. So a lot of the space is not going to be covered. And if you start estimating your score functions, it's going to be accurate for the high regions of image, the top right and bottom left, and it's going to be very, 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 very inaccurate for these other regions of X. And the key idea that linked these score-based models to diffusion models is that it basically found that if you perturb the space of images by adding noise, instead of going something that is quite discrete and high dimensional, you're getting something that is more smooth in high dimensional space. In that case, you can actually have very accurate estimates of your score function across all regions of a high dimensional space, instead of just the regions in which your data lies in. So this step, perturbing by adding noise and subsequently estimating your score functions on a noisy version of your manifold of data, essentially links score-based models and diffusion models. And again, the question becomes how much noise to add, right? You can start with something with very little noise that just resembles your original clusters of data. You can add more noise to some good amount, but if you add too much noise, you're going to be missing out on the actual data distribution. And they basically found that you should just increasingly add noise. Yes. So this is the definition of score function. The score function is essentially the gradient with respect to x log p of x. So this is my p of x, right? In some space, you have high region of p of x, low regions, which is corresponding to where your images actually are. My score function is basically a vector field that from any point within this p of x, it tells me in which direction and how much to move so that I can get to high regions of p of x. That's what gradient essentially is. So at some point, I should move towards there. So I should move towards this peak. At some regions here, I should move towards there. That tells me to move towards this peak. So where to move is basically the gradient, and log basically just normalizes. Instead of having to spiky into something more smooth. Yes. So essentially, these folks, their motivation was that. So this kind of score matching. So learning, for example, this function. Learning actually solving this problem is actually not trivial, but there has been established ways to solve it. But even if you solve it based on established ways, they basically found that going to high dimensions, there was this issue, right? There was this issue that we go to high dimensions, no matter what solver you use from back in the days, you're still gonna get inaccurate estimates for regions in which your data doesn't lie. And adding noise just helps you kind of fill in the gaps. It basically fills in the gaps of regions of low density by actually seeing because you like, let's say these are your real images, right? And this is all Gaussian noise. You basically want to smooth it out so you can get samples that are still close to original, but with some noise, right? So you can think of it as some smooth version to better optimize your score functions.
Yeah, so that's what I was trying to say. So it just sounds like a new kind of like virtualization of the objective functions.
Yeah. Yeah, but that's good insights. And they basically found that you can slowly add increasing amounts of noise. And subsequently, at every amount of noise that you add, estimate the score functions. They're going to be doing much better than just estimating a score function on the original image. So basically, instead of just learning S theta x for the original data, parameterize it by I, where I tells me some amount of sigma I, which is a variance of noise to add. Right? And again, they found that you should add less noise at the beginning and slowly add more noise at the end. And your objective function basically becomes learning the score matching objective, minimizing the mean square error between what you estimate, your score function, at time step I, with that amount of noise, with the actual score function with that amount of noise. Right. And basically find that works really well, right? And that basically kind of gives you diffusion models, right? You're basically also adding noise, small amounts to large amounts of the data, and your score function estimate can be seen as removing the noise from the data. All right, so that's an example of starting from noise and slowly removing the noise to get back your images. Okay, and one very, very quick thing I also want to mention, which is subsequent innovation, is that we saw diffusion models and score-based models by adding noise in a discrete manner, right? Adding one time step of noise at a time. You can also generalize this to a continuous manner. So instead of doing diffusion process through discrete steps, just continuously add noise. And this can also be seen as a discrete sequence of adding noise, but the limit of the number of discrete steps going to infinity. So they basically found that if you do that, instead of having a discrete sequence, you're basically solving a continuous time differential equation. I'm not getting into details of how to solve it, but essentially this actually gives you higher quality samples, exact log likelihood. You can solve the differential equation exactly, and better controllable generation. Right. So over here, instead of having discrete steps of adding noise, you have a continuous sequence of adding noise as given by a SDE. And the reverse SDE, which you have to solve to learn your parameters, can also be computed in some efficient manner. Right, and there are some examples, right? You can see that they give really, really, really high quality samples nowadays. So diffusion models are good. I think a lot of what we care more about is how to condition these diffusion models, because you want to condition it on some like latent variable, some other modality, and so on. So the first way of conditioning them is to just train them with conditional information. Instead of estimating P of X across the real data to the noisy amounts of data, you're just going to learn my P of X given Y, right? So that basically amounts to, again, P of XT. That's my final latent variable. That should be isotropic Gaussian. But each of these intermediate transitions should be XT minus 1 given XT. So a less noisy version given a noisy version, and the label that you want to condition on. So therefore, you can easily extend any of the three interpretations of diffusion models. You can do conditional original image prediction. So try to predict X0, my original image, given some noisy version XT at time step T and the label Y. I can do conditional noise predictions to try to estimate the initial amount of noise added given XT and time step T and Y. Or you can do conditional score function estimation, estimating not just the gradient of log P of XT, but estimating gradient log P of XT given Y, right? So you can basically condition your other variable at any time step. And that's actually how a lot of these kind of state-of-the-art DALI 2 methods work, right? Essentially, you're first training a clip encoder, and this I'm just revisiting this slide from the first overview of generation. You start by these images, you train a clip encoder that already maps you into a semantically aligned image and text space. You have some paired data from text to images. You're going to learn a text encoder, an autoregressive model that maps from text space to image space. And finally, when you go from image space, that's your latent variables, you train the diffusion model that we just talked about back to the actual image, right? So that's where the diffusion model comes in for things like DALI 2. And DALI, the original version was just that you didn't use clip, you didn't use diffusion models, you just train like a variational autoencoder on lots of images. And clearly using clip to get a better space and using diffusion models to get a better generated images improves upon DALI quite a bit. Another thing people might have seen recently is stable diffusion, right? And the key idea in stable diffusion is to basically combine diffusion models and some of the other methods that we talked about, specifically autoencoders. So basically they found that one shortcoming of diffusion models is that you're typically running it in pixel space. You're adding noise from the original image in pixel space. So the dimension of your latent variables is always going to be pretty big, right? You're adding noise and removing noise in pixel space. They found that you can also do diffusion process in latent space. And the key idea is that you first use autoencoders. Autoencoders are good for perceptual compression, so going from high dimensional to low dimensional space. And diffusion models are good for semantic compression. So you're going from low dimensional space to slowly adding noise to it to get a latent variable and slowly reversing noise also in latent space through a diffusion, reverse diffusion process. And that's what the architecture looks like. You have X, that's your raw data, pixel space. You first learn an decoder, so that compresses your data X to latent space Z. And once you're in data space Z, you can do your forward and reverse diffusion process. Right? Z going from Z0 to ZT, which should be isotropic Gaussian, by adding noise and by denoising from your Gaussian back to your final clean data, or at least clean latent variable Z. And once you have Z, you can learn the decoder back to my original pixel space. So combining variational autoencoders of pixel space with diffusion models in latent space. And they also show that you can condition on semantic maps, text, representations, images. And their way of doing it was basically with paired data, nothing fancy. They took all of these what you want to condition on, learn some representation, and basically learn the cross attention between what you want to condition on every time step with the latent variable at every time step as you're denoising it. Yeah, so two key ideas: combining autoencoders to compress from pixel to latent space, doing diffusion models in latent space, and also conditioning using paired data in your latent space. And subsequently, yeah, stable diffusion gets really good results. You can condition on text, you can condition on semantic layouts, you can draw different semantic maps, and you can generate realistic images. You can condition on layouts. You want the person to be here, you want the chair to be here, you want the background to be here, and so on. Right. So that's the first type of conditioning. Basically, if you have paired data, you can modify the diffusion model to take in some external conditioning variable, like text or layouts or semantic maps. That's good if you have paired data and you're willing to just train a model from scratch with this paired data with the conditioning. We also saw briefly another type of conditioning, right? And that was conditioning using classifier guidance. You can basically, using Bayes' rule, write my gradient of log p of x given y as the unconditional score, so just p of x plus the classifier gradient, p of y given x. That's just Bayes' rule. And the multiplication became addition because we're working in log space. And we saw a quick example of this, right? If you have some pre-trained model that's p of x, it can be autoregressive, diffusion models, anything. You can first generate a couple of options for your completion. And let's say y is sentiment, right? Some of these words are going to be positive sentiment. Some of these words are going to be negative sentiment. Essentially, you want to ascend this space when you start out with some data point. You both want to increase p of y given x. So how likely you are to generate something that fulfills your desired sentiment. And you also want to ascend p of x space. You still want to generate something that is realistic in the space of natural language or image completions. So likely you will choose something that's delicious, right? Both high p of y given x, y is plus 1, and also high p of x, right? Because the food tastes shiny is a low p of x, and the food tastes delicious is a high p of x. So likewise, you can also do this for diffusion models. You can also do classifier-free guidance. Just by rearranging a previous equation, if you don't want to train some other classifier, you can instead just express this as a conditional score. So a conditional score and unconditional score, where you have weighted averages of each other, right? So essentially, we want a condition on some latent variable y, learn a conditional variable, a conditional model, and a model that is unconditional. And this seems like you got to train two diffusion models, right? You got to train a diffusion model that depends on y, that takes in y as the input in latent variable space, and also train an unconditional diffusion model p of x. But people found that you can just train one diffusion model, and to get this, you can just set y as some constant or y that is outside the space of the y's that you care about. And there's a paper called Glide. You can check it out. It basically did empirical analysis of all these different ways of conditioning your models, and they found that this classifier-free method seems to be the best. So yeah, to recap, we just added diffusion models to our arsenal of generative models. Diffusion models typically have really high sample quality, but one issue right now still is that they're quite slow to sample with. Right? So if folks have played with stable diffusion, as compared to previous like VAEs and GANs, you got to do this denoising at every time step across multiple time steps before you actually get the clean image. So it's going to be quite slow to sample from. I'm going to have some references. I'm not going to have time to get into it, but usually a mix. Back when GANs were still there, people used inception scores. So for example, how high a likelihood, like if you had a separate trained image classifier model, how high a likelihood that model assigned to real images versus fake images. And I call it inception score because the model they used to test it was called the inception model, some convolutional model. But nowadays for stable diffusion, it's clearly at human quality. So I would like to say a lot of the testing is based on some human evaluation. But still, I'm going to get into the open questions. And the answer is that a lot of these seem good on the surface, but there's still like very easy ways to figure out errors in these models. Right. So these are generative models. But I think what's more important is also how to condition and control these generative models. And we saw quite a few in the last 3 lectures. We saw disentanglement, right? Ideally, it's always good to learn disentangle latent variables that each have some semantic meaning over learning just a huge set of latent variables. And we saw how you could do disentanglement of VAEs using this KR regularization, making sure the latent variables actually follow some Gaussian, and perhaps you can also add some supervision to each of the latent variables. We saw conditioning, very easy. You have paired data, you can learn P of X given Y, and that holds for any of the generative models we talked about if you have paired data. If you don't have paired data, or you have very little paired data and you want to do something specific to language models, you can do prompt tuning. So adding some other external conditioning information through some adapter into language model space and freezing the rest of the language model. You can still get the language model to start attending to these images, for example. We saw representation tuning. If you could open up some of these models and they happen to be transformers, you can add external modalities into the attention layers, right? And get this final representation that's based on both the pre-trained model and the other information that you want to condition on. We saw conditioning by classifier gradient, right? Using Bayes' rule, basically learning a unconditional model, P of X, with some gradient from the classifier. So increasing the model towards high regions of P of Y given X. And we also saw classifier free tuning. You can basically learn a conditional model and some unconditional model and combine them. But in practice, you can just learn one model where for this case, Y is just some other constant. A lot of open challenges, right? We saw creation, right? If you want to take something and generate many modalities at the same time while being coherent, it basically requires you to ensemble perhaps generative models for each of these modalities while fine-tuning them to be coherent across the modalities. That's a big open question. So that's synchronized generation over multiple modalities. Another question is, what is so special about diffusion models from a multimodal perspective, right? Is it just useful because at a pixel level, they generate really, really high quality data? Or is there something special about the latent space that they learn that makes it easier to do fusion and alignment and so on? There could be, because we saw from stable diffusion, they basically look at variational autoencoders that are better at compressing perceptual, right? Low-level features. But they also claim that diffusion models are better at compressing semantic features. So something about how diffusion models learn a better semantic space than other generative models. Some big errors, like some of you might have seen that you can take DALL-E, you can generate some compositions, but they really start failing for novel compositions, right? Weird combination of different objects. So how can you better integrate generation, reasoning, all that stuff in reasoning that we talked about to enable better compositional generation? Better representation of fusion and alignment. Almost all the works that get state-of-the-art multimodal generation, they're still doing like simple concatenating or self-attention to attend to other modalities. It seems like there should be space to use better representation of fusion and alignment methods from the first half of the course, right, to improve generation. And finally, better, or second last one, better control. Can we do more fine-grained control? Can we do more few shot control of these large generative models? And finally, human-centered evaluation. Again, it's very hard to evaluate these methods. I mean, people are organizing workshops, submitting papers on how do you incorporate the humans in a loop to evaluate these generative models, and how do you do that in a scalable way so that you can get humans to evaluate them as when you are training these models instead of just towards the end. But yeah, more resources. All these resources are from good blog posts about generative models, diffusion models, and so on. Cool. Any last questions about the generation before we move to transference? Yes, we actually saw that there is an equivalent interpretation where the first interpretation that we derived was that at any time step t, you add a noise to get an xt, use xt to recreate the x0, the original image. But you can also show that with some equivalence, at some time step t, look at how much noise was added and try to construct or recreate that amount of noise. So that's, as you mentioned, basically estimating a noise at that time step, right? And these are actually equivalent, right? You can, if you can recreate the data, you can do a subtraction to get the noise. You can estimate the noise, you can subtract off the noise to get the data. Yes, any more questions about generation? Cool. So the second last challenge is on transference, right? So in transference, the whole idea is that you have some modalities that are low resource that you care about. You have low resource, either limited data, limited labels, noisy labels, and so on. And how can you use some other external modality to help me in learning a prediction model on that low resource modality? I'm going to talk about three things, three sub-challenges. The first one is transfer. So let's say I care about predicting based on this triangle modality to one. And that has very little data or noisy labels and so on. How can I use some other higher amounts of data or higher amounts of data trained models to help me in this classification? That's transfer. We're also going to talk about co-learning, where if you have a model that you care about predicting a triangle, how can I use some other data to either help me at the input space or help me at the output space, right? And we're also going to talk about model induction. If I have two separately trained models, how can I share information between them So both of these models get stronger. They leverage information from each other. So the first one is transfer, right? The classical setting is that you have some modality with large amounts of data, right? Same language, think a pre-trained BERT model. The knowledge either comes in the form of the data or in the form of the parameters trained within this model. How can I adapt it quickly to help me solve some other modality A, which is less resource, right? So this final model that you get is going to be a combination of both A, the modality that you care about, and the external supplement from modality B. And we've actually seen some examples of this, right? There's a lot of overlap between generation and transference because this modality B can be any large-scale generative model that's unconditional. It can be a big diffusion model, big language model, and this modality A may be some conditioning variable or some image that you or some text that you want this big model to be conditioned on. So the very first part is basically just transfer via pre-trained models. You can transfer via adding it to the prefix. If you have some big frozen language model that contains lots of information, you can start adapting it using some low resource text image pairs. And you can very quickly learn this combined representation that combines the pre-trained knowledge from these large language models and then also the small amount of conditioning information which you want your task to solve. As prefix tuning, this is all representation tuning, right? If you had a big pre-trained model that contains lots of knowledge, if you wanted to get working for some multimodal tasks, you can basically integrate the other modalities in the attention mechanism, right? By basically shifting the representation from your pre-trained space to some space which includes the multimodal information. And again, all these things that we talked about, all these things kind of straddle the line between generation and transference. Generation, if my P of X is some generative model, and you want to condition these pre-trained generative models, but also transference, if my P of X is some prediction model, like BERT language models, and you want to condition them on some other modality. Right. So straddling a bit of generation and transfer. And when you think about transfer and pre-trained models, there's also this new era of doing multitask pre-training, right? Instead of just training on one source of data, you also want to train models that are huge across many sources of data. And recently, people have shown that this is possible, right? If you have one task that involves language, video, and audio, your three modalities for video classification, and then some other tasks involving audio and video for sentiment and emotion classification, and some other some other data set for video and time series for robotic classification, people used to train one model separately, right? There was no transfer between them. But people also recently found that you can train one single model across all of them. And the benefits of training one single model is that you can then share information and generalize very quickly to tasks that have less data than the others. And it's actually surprising that you don't actually need a lot of modifications for this. You can just take all your data from different modalities with some overlap between your tasks, standardize them as some input sequence. So we'll look at language as a sequence of tokens, video as a sequence of frames, audio as a sequence of spectrograms, time series as a sequence of time steps. I'm just going to standardize them into input sequences. I'm going to add some modality-specific embedding. So some embedding layer that basically identifies that this is time series data, that these two embeddings are video data, and those two are audio data. These are basically one-hot embeddings, but trainable. I'm going to apply some shared multimodal model. So in our case, we use a transformer model. And I think in most cases nowadays, you use some generic model that has unimodal transformer layers and cross-modal transformer layers. So anything that you saw in the contextualized representations lecture. And then you can start training these in a multitask manner, right? One output classifier to predict the robot dynamics, one output classifier to predict sentiment and emotions, and one output classifier to predict the category of your video. You can train all of this using multitask learning, right? By basically updating the parameters wherever they're involved. Right, so if you're training this, you update the model and the modality-specific embeddings, and also these other embeddings for video would also be updated. So it's actually really cool. You can use the same model architecture and moreover, same parameters because you've trained just one model. So it shares parameters for all of these tasks to solve multiple tasks at the same time. Yes, so specifically this model, like other multimodal transformers, they take in pairs of modalities. If you have three modalities, it will encode this pair, and the 1 and 3 pair, then concatenate them using your cross-modal attention. So at any time, if you have any number of modalities, you have at least two, right? So you have two, you just use a cross-modal attention. If you have five, you just use like 5 choose 2 cross-modal attentions to encode them. Yes. So the first question was, how do you deal with data sets with many modalities? And that's a great question. I would like to answer that question, but we don't have many data sets with many modalities. So a lot of the data sets are 2 or 3 modalities, as all of you have seen working with the course projects. So right now, just because there's 2 or 3, there doesn't seem to have this problem of suddenly having 2 modalities, suddenly having 10 modalities. The other question that you asked is catastrophic forgetting. So we don't really train this in a sequence, right? We train them, we iterate across all modalities, right? Go through all these data sets. That's one epoch, and go through all the data sets another epoch, right? So we're not doing like continual learning or something where you don't really see data sets way into the past. But that'll be interesting to explore. And the third question was, can you just train on all the YouTube videos, right? Well, people have shown that. People have found that, I think, one of the very few iterations of multimodal deep learning back in like 2012 was when like Google and Andrew Wang's group at Stanford just trained a model, like a VAE type of model, on a bunch of YouTube videos. And they could recognize cats and dogs, but nothing out of the ordinary. And people here also have shown that, recently have shown, and I'll get into that next lecture, that you can actually train a lot of videos, and you can do well on certain tasks like VQA, VCR, but still that's the 2 modalities, video, audio, maybe text, but you still don't really solve AI, right? There's a bunch of things that you need on top of just black box pre-training and getting it to work on VQA, VCR, and so on. Yeah, but I think any of the 3 things that you said are open questions, right? How do you, first of all, have good data sets with many modalities, and how do you train such a model with huge disparities in modality numbers? That's a good question. Another good question is that, is multi-task training the best way, or continual learning can be better? And if you have the resources to train a model on like all the videos, that'd be super cool. But I'm also excited about what your model will end up learning on all the videos. Non-parallel is just a fancy way of saying that your input subset is different at each time, right? So sometimes you have, like let's say you have like 10 modality embeddings overall in your expanded union of all your modalities. Sometimes you see 2 of them, sometimes you see 3 of them. So you only update the subset of modality embeddings that are relevant to the data set that you're currently training on. Cool. Why don't we stop here? I think we're out of time, but let me go into a bit of all this and more pre-training stuff next lecture. But thanks everyone.